For recitation number 5, question 4A and 4B and 5A and 5B, and then question 6, they're all related, and they give us the information that we have two wavelengths of light. We have UVA and we have UVB. And they say that UVA is a wavelength of about 395 nanometers, and UVB is 315 nanometers. It asks us a series of questions to find the energy of both of those, then the energy per mole, and then to compare those energies relative to the energy of a chemical bond. So do a lot of the same calculations for both of those wavelengths. So we're going to do the first part. We're going to do question 4A first, where we know that UVA is 395 nanometers. And the calculation for UVB is identical, except for we have 315 nanometers. Well, the first step to find energy, right, the only way we know how to relate the energy is we know energy equals Planck's constant times the speed of light divided by my wavelength. I chose this equation because I already have wavelength. I have wavelength for both UVA and UVB. So I need to use this wavelength to find the energy of this light. The first step, I need to go from nanometers to meters because C is the speed of light, 3 e to the 8th meters per second. So I know that in 1 meter, right, I have 1 e to the 9th nanometers. That's the same for both of these. So in 1 meter, I have 1 e to the 9th nanometer. Take a look at my units, and nanometers cancel out, and I'm left with meters. So the unit of wavelength in meters, I have approximately 3.95 e to the minus 7 meters is this wavelength, and 3.15 e to the minus 7 meters is this wavelength. Now I can find the energy because I have my wavelength, right? So energy equals Planck's constant, 6.626 e to the negative 34 joules times seconds, times my speed of light, 3 e to the 8th meters per second, all over my lambda, my wavelength. So all over 3.95 e to the minus 7 meters. Same calculation here. Energy equals my Planck's constant, 6.626 e to the negative 34 joules times seconds, times my speed of light, 3 e to the 8th meters per second, all over my wavelength of 3.15 e to the negative 7 meters. We do that calculation, take a look at our units, and meters will cancel, and seconds will cancel. And that's good because we're looking for an energy, right? So our units that should be left should be energy in joules. And so the energy for 395 wavelength light and the energy for 315 wavelength light. Do that calculation for both of those, and I should get an energy of approximately 5.03 e to the negative 19 joules for 395 nanometer light, and then for the 315 nanometer light, I get approximately 6.31 e to the negative 19 joules of energy. 3 significant figures for both of these calculations because in both of these wavelengths I have 3 significant figures. 395 and 315 are both 3 significant figures. For the next step, so this is 4A and this is 4B. For the next step, for 5A and 5B, we're asked to find the energy in terms of joules per mole. And the trick is that the energy we found is joules per photon. 1 photon of light with this wavelength has this energy. So for question 5A, and 5B, again, it's the same calculation, except for I have the energy for from one photon, 5.03 e to the negative 19 joules, and that is for one photon of light. I'm looking for energy in joules per mole of light. So to convert photon per energy per single photon into energy per mole, right, I need to have 1 mole of photons, and I know Avogadro's number, 6.02 e to the 23 photons. Right, that's going to let me convert the energy per photon into energy per mole. We take a look, and moles, when I multiply, will be left. Right, photons cancel out. Set up the same calculation for 315 nanometers. I've got 6.31 e to the negative 19 joules, and that is energy per photon. Again, I'm going to multiply by 1 mole of photons, so it's going to have 6.02 e to the 23 photons. And again, photons cancel out, and I'm going to be left with moles, right, joules per mole for both of those calculations. So I calculate across, I get approximately 3.03 e to the 5 joules per mole for UVA. And I get approximately 3.80 e to the 5 joules per mole for UVB. Right, this is UVA and this is UVB. So there's the energy of both of those. 3.03 e to the 5 joules per mole for UVA and 3.80 e to the 5 joules per mole for UVB. Now for question 6, which one of those is a higher energy? Which one of those should we be more concerned about with respect to the potential for causing damage to our skin, causing damage to the cells in our body? And I give you the hint that the average chemical bond is about 374 kilojoules per mole. That's the average bond energy. Well, let's take a look at these and compare these to the average bond energy in kilojoules per mole. Let's convert joules into kilojoules. And to do that, we would see that, right, I have 1,000 joules in 1 kilojoule. So I need to divide both of these by 1,000. Right, UVA has approximately 303 kilojoules per mole of energy, whereas UVB has 380 kilojoules per mole of energy. So we can clearly see that UVB has more energy, and then why should we be worried about that energy level? If we look at the energy for your average chemical bond, right, the average chemical bond is about 374 kilojoules per mole. UVB is actually greater than that energy, which means UVB potentially contains enough energy to break your average chemical bond. So that's what I was looking for part 6, was just kind of comparing those energies and then comparing those energies between UVA and UVB and comparing that to your average chemical bond strength to see, right, this is why UVB is more dangerous than UVA. It's on the same scale. It's very close to the same energy that would be required to break your average chemical bond.